Hello, everybody. So welcome to this session about the big.LITTLE and an update on the MP development. So I'm Vincent, Guittot. Morton is with me. We are working on that topic, and Amit also is going to join us. So for this session, we'll give you an update of what have been done, what we still need to do, and to give some short status. We also have some questions, some open issue, and I think that this session is a good place to discuss that point. So I think now we can start. We are a bit late, so let's start. So we have 5 main sections for this session. We will start with a short status. Then we will explain what is the policy of our big.LITTLE MP system. We'll discuss about the patch we have, which one are under review, which one are under test. We will point out mainly 2 main issues we have currently. So we don't have, let's say, one solution for this issue, and we would like to discuss that point with you. And then we will go back a bit more in the detail of the HMP, what is the behavior for when we have a low load situation, when we have some web browsing use case, and so on. So if you have questions, don't hesitate to ask during this presentation. You want to add something, Morton?
I think that covers it pretty much.
So for the status, so right now in the Linaro kernel, we have what we call the old HMP patch. That was some patch that have been developed by Morton, and that was the main goal was to make a proof of concept of what could be done with the big.LITTLE platform. Where should we put long-running tasks, short-running tasks, and so on. This was quite big.LITTLE focused, with some hack in the scheduler, and now what we have tried to do is to make that more, let's say, not HMP focused, but any SMP multi-core platform, let's say, generic. So that's why, yeah, this new patchet have not been designed only for HMP, but for any kind of system. And we hope that this will give some improvement for normal SMP platform as well. So all the patches are under internal review and test. So they are currently tested and reviewed by ARM and Linaro. Nevertheless, these are available in public Git tree in Linaro. So anybody can have access to this patch and make some tests if they want. And we have some first results which shows some performance quite close or at the same level than the old HMP patches. So it means that we will keep the same performance, but the goal is to be more generic. So we will have a link to all the patch in the next slide. We still have some use case where the behavior or the task placement, how can I say that? So there is no simple solution for a situation where, for example, we have how many threads as the number of core in the system. Where should we place this task? Because we have big and little, should we put more tasks on the big and let some little idle, or should we use all the core? We don't have one straightforward answer to that, so we would like to discuss that point with you today. And we also have another point, which is which kind of task we should put on big core, on little. So should we put some long-running tasks with a low priority on a big core, or should we keep them on the little core just because it generates some background task? But when we look at the behavior of some framework like Android, you can be in a situation where let's say, we need some performance for this background task. So that's another point we want to discuss today. If you have questions, don't hesitate to ask. So this is for the status. So now we can go, So for the policy, our goal for HMP is to be quite simple in the policy and don't try to have some complex large matrix decision algorithm. So we have keep only 3 simple rules, which are: we want to pack all the small tasks in the little core, at least in the little cluster and in only one little core, if we can, if it's possible. And we want to do that at wake up, just because these little tasks are waking up and sleeping a lot. So the wake up is the most straightforward path to just move that or keep that task on the little core. That's the main point. So once we have put all these small tasks, all this background activity on the little core, what we want to focus is that when we are doing this load balance, this periodic load balance, or this idle load balance, we will go back to that a bit later, we want to focus on the long-running tasks, because we know where we want to put this small task on the little core, and just because they are waking up frequently, we can catch them at wake up and just go straight forward and put that on the little. So when we are doing this periodic load balance, in which we are looking all the cluster, all the core, just to check which cluster is balanced or not, we want to focus that on the long-running task, and essentially to be sure that this long-running task will run on the big core when necessary. And we have one last point, that is to choose the core with the best capacity. So when we have only one long-running core or one small task, long-running task or small task, we want to choose the big core, because we are in a situation where in an SMP system for now, whatever the core is used when you have only one task, it will be the best core. In our configuration, it's not the case, and we want to use the one with the best capacity. So with these 3 simple rules, we are able to schedule and to place the task on the right CPU for, let's say, 90 or 95% of the use case. And we have few modifications in the scheduler. Now we still have some few issues that we will discuss a bit later, which can make these 3 simple rules a bit, we can add some new rules to that, maybe. But we clearly want to focus and keep that simple, just because if we try to make that complex, we will be in a situation where we'll waste a lot of time looking for the best CPU. And we don't want to make that, and to have a lot of things to configure to be sure to have the right behavior. Morton, you want to? Don't hesitate to.
No, I think that pretty much covers it. The goal is really to keep it as simple as possible, because we are messing with a very critical path in the kernel. So it's quite important that it's fast to make the decisions, and also trying to keep a rule simple, so it's easier to understand what's going on, so we don't have to debug massive, complex decisions to figure out what's really going on.
So we can start with the different patch we have. So right now we have 2 kinds of patch. We have some few fixes that have been found while testing the scheduler with the HMP platform. We have mainly three patches which are fixed. The one is, the goal is to remove some spurious trig of the idle load balance. So right now in the scheduler, you have some field that, let's say, keep the number of busy CPU in a system. This is used to trigger load balance in a cluster or in the system, just to say, okay, if we have several running core or busy core in a cluster, we should trigger load balance to be sure that the tasks are well balanced in a cluster and then in the system. So the initialization of this value was wrong, just because of some, let's say, synchronization issue between the skate domain configuration and some specific atomic value. So we have a patch for that, which is, so we have a new version which is under preparation. We have a lot of issues to be sure that this skate domain, which are RCU, will be synchronized with some atomic internal value. So it was quite difficult to find a solution that will work for everybody in all the use cases. We have another patch which is about, so all our work is based on the per task load tracking patch that have been pushed by Paul Turner. And during our tests, we have found that the load average of a core can be corrupted if only one real-time task was running on this core. In fact, the goal is that all the load average tracking is done into the CFS scheduler, but if you have only one RT task running, you don't have any call to CFS callback, and you can be in a situation where the update of the statistic gets wrong. And the last one was for active migration, because that will be one feature that we are using with big.LITTLE to actively migrate a task from the little cluster to the big cluster when needed. And we have found that in a situation some field was not initialized and it was impossible to migrate. When you have only one running task on a little cluster and you want an active migration, some field initialization was missing. These are three fixes that so they are under review, and the goal is to make that more stable for us. But that's not let's say the main patch for our platform. It's just some needed fix for us. So for the load balance part, so we have, let's say, 6 patch set, 6 series. The first one is packing the small task on few core. So we have already pushed 2 versions. We have another one which is under review and under test. And the goal is clearly to pack all this background activity on few core. So for the big.LITTLE architecture, we want to put that on A7. So we need to publish this new version with new update. We have made that more, let's say. They had some discussion about the impact for NUMA system, and we believe that we should stay focused inside the node, and we should not compete with the NUMA load balancing. So the goal of this packing small tasks is just to pack in one CPU, in one node, and let the NUMA load balancing do its job across the node. Because it's not so simple to migrate. You not only need to migrate a task, you need to migrate a memory as well, and we don't want to compete with that. So we just need to focus on packing in each node, and we'll let the normal or the NUMA load balancing doing some load balance across the node. So we also need to use the per task load average, but right now this is only enabled for when you are using the C group and the sched_fair configuration, where you can group some tasks to be seen as one single task by the scheduler, and you can make some scheduling inside this group. So we want to use this per task load average tracking not only for the sched_fair group configuration, but for any kind of configuration, because we need to filter which tasks are these long-running tasks that need a lot of capacity. So we have used some patch have been pushed to enable the per task load tracking in the normal scheduling behavior. This have been pushed by Alex Shi, so we are using that because we have done that, and that's exactly what we need. So we are keeping this. It's 4 or 6 patch that have been pushed. We are also using a feature that is currently available in the kernel, which is load balance min feature. And the goal is that the periodic load balance should balance the long-running task in priority, because this task will make the difference in a balanced or unbalanced system. We not really need to care of this small task, because it's just, most of the time, it's just some noise in the load balancing. And trying to have a always balanced system when you have some tasks that will wake up for 1 or 2 milliseconds or less than 10 milliseconds, we will just waste our time or keep migrating everything a lot of time. So whenever possible, we want to only migrate this long-running task. But in some case, we will not have other choice that take care also of this small task in the periodic load balance. But that's not the primary focus for us. And using that with the packing small tasks, make that all the small tasks are managed by the packing small task patch at wake up, and the load balancing, the periodic load balance, will use this, will just take care of this long-running tasks that are the one that need some performance. The three last patch are migrate on CPU with highest capacity. So we have some situation where we have few tasks running on a system and even more few long-running tasks. So clearly, when you have a system with a dozen of tasks, a long-running task in an HMP system, in a big.LITTLE system, right now the current scheduler is already ready to handle such kind of situation because the scheduler can have an idea of the capacity of each core. So when you have a lot of long-running tasks, everything will be balanced in the system. You will have more tasks on the big and few tasks on the little. Now, when you come in a situation where you have less tasks than core or the same number of tasks than core, it's a bit more tricky because you must migrate this task on the big core, on the core with the highest capacity. So we have a patch set for that. And we have seen that this situation is also, this is a situation that an SMP system can face. In fact, when you have some, in the scheduler, in fact, you have the completely fair scheduler, and you have some real-time task scheduler. And the real-time tasks are stealing some time to the completely fair scheduler. So from the CFS point of view, the capacity of the CPU is reduced by the amount of time that is used by the real-time task. So you can, in an SMP system, you can be in a situation where you have some CPU with less capacity than other CPU, just as we have in the HMP system. And because we not always know, because if we have only one task, this task will just take one core in this SMP without taking care of the capacity. We can be a situation where you have this CFS task running on the same CPU than the real-time task. Whereas we can migrate that to another CPU that is more idle with more capacity available for the CFS. And in our case, with a big core which have more capacity because it's the microarchitecture feature. So we have a few patches in order to tune the scheduler for the big.LITTLE, but we want to keep that as small as possible. And the main configuration or the main difference is that we want to reduce this periodic load balance in order to improve the responsiveness of the system. But that's clearly, we don't want to have a lot of nodes or value to modify for your system. We want to keep that as simple as possible. The last point is the scaling invariance. And it's one point that right now the per task load tracking patch is only tracking the amount of time you are running on a CPU, whatever the frequency is, whatever the CPU capacity is. So a task that is running on an A7 that is running, let's say, 10 milliseconds on an A7 at 300 megahertz will have the same load from a scheduling point of view than a task running on an A15 at 2 gig for the same amount of time. Whereas they clearly don't need the same computing capacity because on the A15 at 2 gig, you will probably have time to compute or maybe 10 more value than on the A7. So we have a patch for that to be sure that whatever the core and the frequency of this core is, a task will have the same load tracking, the same value, the same load value. So, do you have any question? Or we can continue.
So,
yeah.
how do you assign different load values between the different core models? In a study?
Are we what?
How do you assign different load values for the different core models, A15 and A7?
So at boot we have in our ARM architecture we have push patch which give a computing capacity for each kind of microarchitecture. And when we boot and when we are creating our CPU topology and when we are initializing the CPU power of each core, we use this value, which are just some, let's say, fixed value based on ARM output to say the A15 is twice faster than an A7 for computing some value at the same frequency. So we are using this microarchitecture definition and the max frequency of the core to say that an A7 at 2 gig will be, I don't have the real value, but maybe 10 times more powerful than an A7 and at 500 megahertz, for example. Yeah?
But actually, the load depends on how you load.
Sorry.
Actually,
yeah.
the portion between A7 and A15 is actually depends on the load. So
Yeah.
if the computation is all kind of integer, or all kind of floating point, they are different. So for floating point, let's say CFP maybe 3 or 4 times faster than CS7, but for integers twice faster. How do we deal with this kind of situation?
I'm not sure to have. Okay. You mean the situation where the frequency of each core is different?
No.
Yeah.
So the difference in compute capacity of the performance between F2 and F7 depends on the load.
Oh yeah. So yeah, right now it's not something that we have. We have a static capacity attribution. Yeah, we don't. Right now we are not taking into account if it's a more memory task, or yes, a task that's using a lot of memory access, or a task that is a full computation. So that's we are not using that right now into account because it's an additional point that will implies to use the PMU and so on to get let's say some cache miss and so on statistic into account. That could be something for the next step. Yeah.
So, I don't know if you answer my question. Can you speak up?
Yeah. Can you speak up yet?
Yeah, you were saying before that the A15 instruction contains
Yeah.
So how, if you're doing classes across the world, how do you
I'm sorry, I don't have listened at the end of your question. Maybe there is a microphone you can. Yeah. I don't know, maybe it's only for the Hangout. Yeah, maybe it's only for Hangout. Yeah. So.
Well, anyway, you said before that the A15 can carry out instructions quite a lot faster than the A7.
Yeah.
And how, if the task is split so that the A15 is really quick while the A7 takes longer, how would you synchronize between the two? Have you got to introduce wait states in the A7 tasks? If there's a thread that are out of sync?
Um,
Yeah, but you've got some tasks on B7 or some tasks on B7, part of it being on B15.
yeah.
Is there a wait until the A15 completes before you're on B7? How does that?
You mean when we want to migrate a task from A7 to A15?
Yeah, well, I assume that threading is done such that some of the parts of the task might be on the A7, part of the task might be switched to the A15.
Yeah,
So when it gets switched to the A15, it has to be quick, yeah?
yeah.
And then what's happening with the A7 while the A15 is doing stuff really quick?
What's happened with A7? It will
That's different wait.
yeah.
Yeah, but you've got a task, so let's look at the way around. So a task on the A15 that goes real quick. What is happening with that A7 that did have the task on the switch?
With the tasks that are on A7, they will run slowly. Yeah,
There was a task on the A7 that
yeah,
you switched to the A15.
yeah.
So what's happening with the A7?
It will either another task will be scheduled on the A7 or it will go to idle. It's clearly, yeah, so we will have a session about multi-cluster CPU idle, which explain how we can how we manage the C state of each core and each cluster independently. So what we are focusing there is to place the task on the right CPU, and the power state of this idle CPU will be managed by the CPU idle driver. Now, during the last Connect, we speak also about the latency for waking up another cluster. Just because if you migrate a task from an A7 to an A15, for example, and the A15 cluster was down, you need to wake up this cluster, and that can take up to 1 millisecond. But our goal is clearly that because we want to migrate this long-running task, let's say wasting 1 millisecond to wake up the A15, but in order to have, so it depends of the P state, but twice or 4 times more capacity, it works, but only for this long-running time. Yeah.
I suppose it's early days, yeah. Is there any analysis being done to find out how often that actually happens? Because that 1 millisecond that we talk about,
Yeah.
if it's switched over lots, it's going to a long time.
Yeah.
To me, it's important from a processing point of view, but more importantly, it's a waste of power point of view. So,
The waste of power to waken up and pour down the.
really 1 millisecond generates a second.
Yeah.
This is power.
Yeah. But yes, I agree. But it's always a matter of how many time you want to waste to get more capacity. So that's why yes, we only want to focus on this long. By long running tasks, you mean at least a task that will, I don't run 10, 20, or 4 or 40 milliseconds. So wasting 1 millisecond to run more than 40 milliseconds, it works. But I agree that if we only want to run 1 additional millisecond, we should probably stay on the A7 just because it's more efficient. And from an end user point of view, running 2 milliseconds on an A7 or only 1 millisecond on an A15 doesn't make such difference. So.
Yeah, of course, the other problem is that it's impossible to figure out how it's going to execute. It might execute, you might have switched it to the
Yeah.
it might run for a while. The execution might actually be slow. It might seem fast at first, but then it might go slow.
Yeah.
So at that point, you may have to switch back.
Yeah. Yes.
Use another switch.
I agree. But yeah. So before per task load tracking, the only information we got for a task was its nice priority. Now with the per task load tracking, we have a statistic to the average running time of this task. So let's say we have, yes, we are able to to have a good view of how many times this task will run when it wakes up. For sure, it's not always true because a long-running task can just wake up for a while sometimes. But we don't have so much solution. If a task is waking up and running, let's say half a second each time, and for this time it just wants to run 1 millisecond, it's impossible for us to catch this. So for sure we will have this kind of failing migration effect. But the goal is that most of the time it's true. And even that, let's imagine that this task, which is most of the time waking up for 100 milliseconds, just wake up for 1 millisecond this time. So we will so maybe it's not worse for this, but it will be already there in the A15 cluster for the next running time. Or otherwise we will keep it back. Yes, but for sure we will always have some use case where we will fail to have the good to choose the best CPU target, just because we don't know what the future will be. Yeah.
So, sort of spin off of that. Have you collected traces from real workloads, and you have a model where you can do experimentation like this?
Yeah.
Build a model? Have you used LinSCAD or anything like that to try to build a model of this?
No, we haven't used LinSCAD. We have mainly used now that we have a big.LITTLE platform, and that the per task load tracking is available in the kernel, so we are directly using hardware platform. Yeah.
I guess what I'm asking is, it's really useful to have a model that comes to data through instead of building a kernel, running a workload, getting the metrics out of it.
Yeah.
You have a model that's
Yeah.
I did some early work with LinSCAD, but the problem is that the current LinSCAD version is based on an old kernel by now, and we haven't spent the time to bring that forward. But it is possible to hack LinSCAD to be able to do a simple model of big.LITTLE. The problem is really that modeling complex tasks like the ones that we find in Android is not very easy. So the error in the model might be so big that it's useless. But of course, if you want to test synthetic scenarios where you define by hand that what happens if we have a 10 millisecond task and another 5 millisecond task, and this behavior, then LinSCAD is really useful. I think so, but there are some parts missing in the public repository to actually record the traces. I asked Paul Turner about that, and he wasn't sure if it was right or not that these parts were missing. But I think development hasn't really progressed since he posted the latest LinSCAD version. But yeah, it would be possible to do something, but because we're doing a lot of tests with Android workloads, we've been focusing on running on real platforms and added loads of extra F-trace events to generate statistics to see what's really happening in the system. I trust those numbers more than something I get out of LinSCAD.
We have some trace for some B-bench test at the end of the slide that will show you that it's not as simple as one long-running task and one short task. We have a lot of tasks running simultaneously, and it's quite difficult to simulate. So that's fine.
you're going to have an uphill battle if you're the only user of this feature.
Yeah.
The rest of the scheduler community is working on something else.
Yeah.
You're going to bring some constant, and you're going to have to keep moving your Android to see if they program it.
Yeah, no, yeah. So yeah, all our tests, we are doing that on Android, but also on Ubuntu baseline as well. We are using both. And in fact, it was when we have used MP3 playback on the Ubuntu, that's that's the use case. During this use case, we have found this RT task issue with the load balance, with the load average tracking. So we are not only focused on Android for sure.
To your point about increasing workload coverage is an excellent point. We're trying to ramp up on that, try and get more variety into our workloads that we're testing. We don't want to concentrate just on Android unless we have an enterprise.
That's fine. I mean, but that was not the key point I had here.
I think that we need to go, yeah, faster. So we have two main open issues right now that we want to present to you. So the first one is nice priority and load average contribution. So the load average contribution is a mix of the nice priority and the running time of a task that is used by the scheduler to make the load balance. And we have some situation, so I have put 3 examples that if you take, so in the middle, with the nice priority 0, a task that's running 100% of the time have a value of 1K. But if you take a task that's running only 10% of the time with the higher nice priority, you will have some quite similar values. So you can't make a real difference between these 2 tasks at the end when the scheduler needs to choose one. And at the opposite, if you have a low value for the nice priority, an always running task will have a low load average contribution, which is only 100%. 100. So if you have these 3 tasks in a run queue and you need to choose one, you can face a situation where the last task with a low contribution can be seen as a small task by the system. So does it mean that we should keep that on an A7 because it's a low priority task and we don't really need some performance on that? Or should we detect this long running task but low priority and migrate that to A15? So an example of that is the asynchronous task on Android, which have a low nice priority, but that this kind of tasks are used by bench to detect the performance. So you can be in a situation where, from a scheduler point of view, say, okay, it's a low priority task. We can keep that on an A7 for background activity, but in fact, it will be used to compute some performance values. So it was one of our questions to say, where is the best place to run this low priority task? Should we keep that on A7 or should we migrate that on A15? I don't know if you have some opinion on that, but our first impression was to say that this background low priority task, even if they are running a lot of time, should be kept on A7 because we need to save power and we don't need to get a lot of performance or responsiveness. But we have faced some bench that are using this kind of task to make some performance evaluation. So. Sorry? Yeah. Yeah.
So it surely varies in the applications that you're I don't mean the actual app that you're running, but what it's built into the device.
Yeah, the point is that we can change the behavior depending if we want to make some bench or if we want to do some power saving. So that means that we need to have a knob that with which we will be able to change the behavior dynamically. I'm not sure that at the end user, I'm not sure that he wants to play with that to say, okay, I have just downloaded a benchmark, I just want to make some bench, so I move to this performance, or now it's not a bench application, it's a normal application, so I'm going back to that. Yeah.
The device that they send to whatever magazine is reviewing.
Yeah, but now, if we come back, for Android, anybody can download the bench and run this bench and upload the value. So we will face a situation where the same system can have 2 different performance values. So we need to be, let's say, coherent and that.
That's the problem with bench.
Yeah, I agree.
But
Yeah.
It just can't run the A15 stack.
Yeah.
Unless arguably the A15 takes half the power.
Yeah, maybe that will be the only solution to get. Yeah. Right now, I think everything could be possible. We have a default behavior that is to say this low priority task stay on A7, just because it's the way our current development. That's the current development behavior, but we can change that. We can make that configurable. The goal is to get some input to see if there is an interest to make that configurable or to change the behavior because the other behavior is the one everybody wants to use. We'll continue. Yeah, I'm going to the next. The next open issue is offloading to A7, in fact. So this is an example. When we run some bench like sysbench with 5 threads, for example, this is the TC2 configuration, 2 A15 and 3 A7. So we have five threads running simultaneously, and the current scheduler put 3 threads on A15 and 2 on A7 just because of the capacity of each cluster, which is written just below. From a scheduler point of view, so the 2 A7 have, let's say, 50% more capacity than the 3 A7. So from a scheduling point of view, a balanced system is 3 tasks on A15 and 2 tasks on A7. But at the end, for sysbench, for example, for this test, we are just accumulating the number of events of all the threads, wherever they are. So it's worth using this task number 2 to put that on CPU 2, just because we are accumulating, everybody's accumulating to the same counter. So at the end, what matters is having using how many CPU as we want. But if we have a situation where all these tasks have their own job to do, and we're just waiting that everybody has ended, in this case, maybe it's worth putting more CPU, more tasks on A15 and few tasks on A7, just because the capacity is much more higher, twice, or I don't know, it depends on your configuration. So that's an example. That's another example where we don't have one simple solution, because depending on what you're doing, some would prefer to put everything on A7, to use all the A7 core, or for other use case, we would prefer to keep this A7 idle. So I don't know if you have some use case or much of, from your experience point of view, which configuration seems to be the best for you, for embedded or for server and whatever. Maybe it's not a situation yet. Yeah, so yeah, we are coming to a situation where if you're taking the total power consumption, we must take into account how many times. It depends if it's an ended process to do, or if it's something that will run whatever the capacity you have. So yeah, from a pure power consumption point of view, it depends also of the time used for running that and yeah. it's platforms. It will be platform specific, in fact. It will depend on the max frequency of each core, the leakage, the process. But I think from a power saving point of view, it should be, maybe it should be better to use all the core, because the trade-off between the performance and the power consumption will be quite acceptable. Yeah. We have, I think, we have 3 additional slide set, which are some details about the packing small task, use the best core, and a bbench example. So I'm going quite quickly to that. So this is the result for an Android MP3 playback. The result is similar with the Ubuntu MP3 playback as well, so that most of the load is on the A7 cluster. A15, we see that we are not 100% on the power down state of the A15 just because we have some work queue that are pinned on this. We have some side activity to try to migrate this background work queue and timer on the A7 also. So right now we can see that we have some, let's say, threads that are pinned to the A15 that are waking up periodically. That's why we are not at 100%. But we can see that most of the activity is on A7. And this is another example of when you have a long-running task, 10 milliseconds after this task migrate to the big core just to get the best capacity. And at the end, this is the scheduling of web browser. So we have run bbench on our platform, and you can see the scheduling of all the tasks. So as you can see, we have not only one long-running task, we have a lot of few tasks that are running simultaneously. We have one main thread, which is the web view core thread, which is rendering the page, which migrate on A15, sorry. Then on our platform, we also have some Surface, Flinger, and Android browser, which are running quite simultaneously. And this is the MP3 activity, which stay on an A7. So this has been done with the current patch we have. So it's quite close to what we want at the end, but we still have some few issues with the use case we have just described before. For the C groups, everything is already, in fact, what we have done is the scheduler is just, can be, let's say, we still use the C groups to put a group of tasks and to pin that in a group of CPU. That's always available. And in this case, the scheduler will just try to do his best among the tasks that are available for this, among the CPU that are available for this group of tasks. So if you know that you have this ugly or pulling task, you can just put that in a background C group that will be pinned on A7, for example. That's all right. And I think that trying to make the scheduler aware of everything will be almost impossible, but we have other functionality like the C groups that can help you. If you know that you have some tasks that are background that doesn't need to be used on A15, you can pin these groups and their child on A7 cluster. That can be done easily, and it's only a user point, only user space can do that because he knows that this task doesn't need to use all the capacity of the system. Yeah. Now what we want to deal is just with the common and the, let's say, the normal use case. But that's an answer to say that, okay, I know that I have this background activity, it must stay on A7, and C groups is the best answer to that kind of use case. I think that we have finished. The session is over.
Yeah, time's gone. But
Yeah.
if any of you have any questions, please come and find us and discuss if you have some points or some comments. We're very happy to hear any comments.
Yeah, we will be in the. I don't know if we have a. Yeah, we'll be in our hacking room, in the power management hacking room, so you can come and ask questions or explain that you have some issue with the current patch. You should do that and that. We'll be happy to discuss with you what we have done and what should be done in addition. So feel free to come. And thank you.